Project goal: that every electrician without knowledge in programming would be able to realize automation of the house, cottage or greenhouses, or etc. Unfortunately, not every electrician can program. But, with the help of stm32, we can solve this problem. This stm32 board has Stlink, and when you connect this board to a computer, the computer will detect it as a USB device. At this point, you can see how this code works. The 3 LEDs blinking in turn, and we are going to upload and run code with one blue LED. And if you open the file manager, you will see a connected USB device. It's our stm32 board. If I turn it off, then it will disappear. If I connect a USB device, it will appear in the device list. And to upload a new code into the stm32 board, we need to drag and drop a file with a HEX extension, and that's it. And as you can see, only blue LED is working now. I think any electrician can upload new code to the stm32 by drag and drop the file. Let's flash our stm32 billet. To do this, open a GitHub window and clone our project. Since we work in CubeIDE version 1.13.1, so we must choose the corresponding branch with similar version 1.13.1. The other branches, we're disabling. Here we can see how the project is loaded. Go to the programming window. Open the downloaded project. Once again, check the version of the project with the version CubeIDE. Further in the project, you need to find and open the folder debug because it contains a file with the extension hex. Opening the STM USB drive. And just drag and drop the file, or, as usual, just click on this button to flash stm32 board. I will be doing this as an electrician who has no programming experience. This process will take time a little bit longer than the blink since the project is many times larger. As you can see, the USB is not connected to the stm32 board, and also you can see that the web interface is not available. This is because the stm32 has not received the necessary data from the USB, such as IP address, etc. Let's connect a USB flash drive. USB flash drive should light up. It means that the USB flash drive has the power. Open the serial monitor to find out what IP address, get the stm32 board. Write the obtained IP address to the browser. Whoa, look at this, it's working. What to do if you have a different network? And, do you need other IP address? There is a file for you in the project, which is located in the folder core inc and file named settings.h. The default information is recorded here, such as username, password, IP address, etc. Here you can specify your data, which will be by default when the stm32 is powered up for the first time. What should do an electrician with no programming experience and having only a hex file? First, the electrician needs to format the USB flash drive in FAT32 format and connect it to the stm32. Let's connect the serial monitor, so you will know what's going on. And powering up the stm32. As we can see, the settings.ini file was created and we got the IP address. But the electrician needs to specify his IP address. And the main thing for him is to create the settings.ini file. The file was created automatically, and now turn off the power. Take out the USB flash drive and insert it into the computer. Here it is, our settings file, and it was created at this point in time. And the data is written to it. Open the settings file and copy JSON from it. Open Google and type JSON validator in the search box. Open the first link and paste from buffer the JSON. Press the button Validate JSON. Here he needs to find the IP address and copy the desired element. And using a search bar, it finds the item you're looking for. Replace with the required value. The following IP address element can also be replaced in the same way. Changing the gateway value is absolutely identical. Finds the gateway element and replaces it with the desired value. After making changes to the file, you need to save the file, remove the USB flash drive from the computer and insert it into the stm32. Now there is an edited file on the USB flash drive, and the stm32 will read the new data when power is applied. We got the IP address, and this means that the configuration file was read with the new data. When logging into the stm32 billet, a username and password will be required. You can change username and password at any time in the Web-interféis settings page. By default, admin and password 12345678. Next, you get to the home page, and here you can read the purpose of the project and who we need. And the first item says we need a designer. I think there is no point in explaining why we need a designer. I want to say a few words about it. If you are a designer, but you have no previous experience with stm32, we need you. We, under your guidance, can redesign everything what you see here. We have experience with stm32, but we are not designers. We need a stm32 programmer, because our code needs to be optimized. We need a PCB designer. We want that any electrician to be able to download Gerber files PCB, and then make an order in China. So, let's go. We have the stm32 board, which has 144 pins. Unfortunately, we can't configure all 144 pins for our tasks, because some of them are already used by USB, Internet, etc. But, if we open a select pin page, we will see 89 pins at our disposal. But I think 2 more pins may be added. About 90 pins can be used for our tasks. This stm32 has 3 built-in LEDs, red, blue and green. There's also a blue user button. According to the user manual, I know where they are. Also in this table, you can see switches and relays. Instead of a relay, there can be some controllable device, for example an LED. For switches, we have a button pins page. Nothing has been configured yet, therefore, it is empty inside. For relays, we also have a page named Relays Pins. The relay is also not configured yet, so this page also is empty. Let's configure the integrated LEDs. According to the user manual, I know on which pins the LEDs are located. Green LED on the PB0 pin. Mark it here as LED. Let's see if the entry appears on the Relays pin page. Yes, a new entry appeared here. The blue LED is located on pin PB7. It's also labeling as a LED. He also appeared here with a new entry. And the red LED, which is on PB14, we will mark as LED. And if we look at the list of LEDs on the Relays Pins page, we can see all 3 LEDs that we have marked. We haven't marked the switch yet, so the Buttons Pins page still empty. We have a blue user button on PC13. Let's mark it as a button. And if we open the Buttons Pins page, we'll see a new entry. Let's use the web interface for creating a connection between the button and the LEDs. To do this, we have links to Edit Button and Connection. Let's pull down our blue button. Let's open the button configuration window. And here we just need to select Pull Down. The other elements for customizing the button are not used now, but they are sent from the web interface to the stm32 and stored there in the structure. It is saved after clicking on the Save button. In this window, we can see that our button is now pulled down. Now click on the Connections link. In the window that opens, we can create a link between our button and the LEDs. Let's do that. Save, and you can see there is a connection between our button and LED PB0. Now having a connection between the button and the LED, we can observe this. The green LED should light on or off when the user button is pressed. Let's add blue LED. And we should have 2 LEDs lighting up when the button is pressed. Now, 2 LEDs react when we're pressing the button. Let's add a third, red LED. And now 3 LEDs responding to the push of a button. Let's imagine a situation where you need to delete some connection. Click on the cross next to the desired LED. And now, if you press the button, only 2 LEDs light up. Let's turn off the red LED. And now only a blue LED works. And if you remove the blue LED, then when you press the button, nothing happens. Let's reconnect the red LED. And if you press and hold the button, you'll see how our ugly code working. If you open the main.c file, in it, you need to find the input task. And you will immediately understand why our code we called like that. We tried different ways, and each time we understand that we weren't implementing this piece of code well enough. This is another reason why we wrote in the second paragraph that we need a stm32 programmer. Let's continue. We've seen the home page, we've seen the select pin, buttons pins and relays pins have been looked to. Next page it is a timers. Devices that operate strictly on time are, in our opinion, a necessity for home automation. For example, watering the lawn at certain times, turning on streetlights in the evening, etc. What is cron? You can look up on the internet if someone doesn't know. In short, they are timers. With timers, you can program the switching on or off some of the devices strictly according to the time. On this page, we've created hints how to use the timers. As you can see, no LEDs are currently active. Let's set up the timer. To do that, you need to go here. Let's make the LED blink once per second. To do this, you must write a regular cron expression in the cron field. Below are some different examples of cron expressions. In the action field, you must enter what action should happen when the timer is triggered. I want the red LED flashing every second. We have a red LED on PB14 and it has ID 19. I will explain where I got ID 19 from. Here we write, for example, gazon. In Russian it means lawn. Wrong cron expression, this means that I have entered the wrong cron expression. Our crown has 7 elements. The seventh element is the year. And in our example, the crown has 6 positions. We will correct our hint in the future. We need to add a 7th element in cron expression and it should work. In this window, you can check your record. It says that every second the 19 pin will changes its state. What is 19? I said earlier that I want the red LED on PB14 to blink every second. PB14 has ID 19. And this 19 I have written in the timer. What is a :2? Zero is to disable pin. 1 is to enable the pin. 2 is to change the state of the pin. A colon separates the pin from the action. This example says, pin 18 will turn on at the specified time, stay on for 5 seconds, and turn off at the end of the pause. We have created a timer, but for some reason it doesn't work. It doesn't work because we need to reboot stm32 board for the timer's changes to take effect. Open the settings page and click reboot and the reboot will begin. stm32 board rebooted. We got the IP address, the web interface is up. But, why the timer does not work? Because at this moment, stm32 is getting time from the internet after rebooting. And it needs some time for connecting to the servers in internet. Up to 1 minute. We got the RTC time and the red LED started working. How you can see it is very easy, customize the timer to your needs. Let's now add a blue LED. To do this, log into Edit Cron again. Here we have it written that the separator is a semicolon. Write the required quantities separated by semicolons. The 7th ID is a green LED. And the 13th ID is the blue LED. Then press the Save button. And you need to reboot the stm32 board again. The stm32 board rebooted and we got an IP address. The web interface is raised. And we have to wait again until the web-controller connects to the time servers on the internet. The stm32 got the time from the internet and we see a difference of 3 hours. This can be configured in the web server settings. But, that's not the point now. After receiving the time from the internet, our timer starts working as we have configured it. At the moment, we only have 10 timers. This is because we are trying to save memory. So far, 30.58% has been used and over 69.42% is still available. When we finish the project, we will allocate all the remaining memory for cron tasks. And the number of available timers will increase many times. If you have questions, feel free and ask us, or use our tips. Go to the next page, Settings. Here we have the Reboot button, which we have already used, and the Save Configurations button. On this page, you can change username and its password. You can also change the language of the tooltips. At the moment we have 2 languages, Russian and English. Now the Russian language is active. Let's change the language of the prompts to English. After changing the language, you should press the button to save configurations. To make the changes take effect, Hourly zone selection. All changes are saved on the stm32 in a structure, but as we remember, the ugly code does not use this data. Network settings. Unfortunately, we couldn't realize the settings for dynamic IP address. But everything about static IP address it works property, and you can change them at any time. API settings. API is now used everywhere where there is automation of anything. It is a handy tool, and we have implemented it too. We have implemented a generator, you can use it. I will use my generator. How to use this API? First, let's see what the webcam shows us. The webcam shows to us that our timer continues to work as we configured it earlier. If we want to stop it, we just need to delete it. I removed the timer at the wrong time. At the moment when all 3 LEDs on. But it's okay, it is not a problem. Back to our API. It works like a normal GET request. I wrote a hint for you. You need to paste this link into your browser, changing only the token, ID, PIN, and action values. Replace the token with your value. In my case, the value of the token is ZERG. Specify the required PIN ID. In other words, which output you want to control. For example, I want to change the state of the red LED, which is on PB14, and it has ID 19. Red LED, and specify what kind of you want action. The number 2 indicates a change of state. For other options, visit the timers page. 2 is toggle. Copy our link and paste it into your browser. Look at the red LED. Press enter. If you refresh the page, the request will be resent and the red LED will change state. As you can see, the API is working as it should be. MQTT. MQTT works, but remember the ugly code that doesn't use any of this data. I have an MQTT server installed on my Synology with this IP address. I have the default port. I don't need client. I don't need user either. I don't use password. I wrote Заготовка as an example. After changing the variables in MQTT, you must save the changes by clicking the Save Configuration button. And also you need to reboot the stm32 board. Open the serial monitor. And see what it writes after the web interface comes up. We got the IP address, and immediately after that it says that MQTT connection, successful connected. This means that the MQTT client connected to the MQTT server successfully. Next one it is coordinate settings. Longitude and latitude. Sunrise and sunset. The idea is that the user specifies their coordinates, and the stm32 board calculates sunrise and sunset and showing here. It would be great if sunrise and sunset calculation could be done on the user side. But the user will use the web interface very rarely, and recalculation should be done every day. Therefore, this math should be done on the side of stm32 and here output only information according to the entered coordinates. Okay, it's all over now. In the future, we plan to add one-wire protocol. In our opinion, this is the optimal solution because we can connect up to 255 sensors of DS18B20 on one wire. This will be cool, right? We can also easily add protocols like Modbus, CAN or others protocols, but if it makes sense to do so.
Your code is the worst I've ever run. But it did run.